Swayam Prabha. Digital India. Educated India.
So today we continue with the problem that we were solving last time. Also, we will complete the topics that are left in the fault calculations using symmetrical components, and then we will move on to the next topic, that is the first paradigm in protection, that is namely overcurrent protection. So this is the problem that we were solving last time. There are two sources and two transformers, a transmission line in between, and we are supposed to calculate the faults at G, buses G, H, and also the midpoint of the line. So we will continue. There is a slight error. Last time this is 0.05 ohms, or 0.05 rather 0.05 pu, not 0.5 pu. Okay, so we will make that change and continue with the problem. Okay, so these are the three. This is the positive sequence network, this is the negative sequence network, and this is the zero sequence network. Now we will calculate the Thevenin equivalent networks rather. To calculate the Thevenin equivalent, we will short the two voltage sources first, and then calculate the equivalent impedance. So if we short this, then we will have, for the bus G, fault at bus G, then we will have this 0.1 plus 0.05, that is 0.15, in parallel with 0.24 plus 0.1, that is 0.34, plus 0.3, that is 0.64. Okay, so let us draw that. I am deliberately leaving this gap. Okay, or we will not leave that gap. So this is 0.15 as we said. This is 0.15 is 0.1 plus 0.05 here, and then this is the bus G here, which is the faulted bus, and that the parallel with that is 0.24 plus 0.1 plus 0.3, so 0.64. Okay. The negative sequence equivalent will be the same because the per unit impedances are the same, 0.15 pu, 0.64 pu. The zero sequence is however different. Here if you see, it is 0.05 in parallel with 1.1. Okay. So we have 1.1 pu, and the since both the sources are 1 pu, then we can just replace it by an equivalent source of 1 pu and then connect it to the common reference. Since there is no fault impedance, we just connect it to the common reference. This diagram is also incomplete because it has to be connected back to the reference here, reference bus rather. Okay. So So, now these two 0.15 in parallel with 0.64 will give you Z1 is equal to 0.15 into 0.64 upon 0.15 plus 0.64, which is equal to 0.12 pu. Similarly, Z2 being the same impedances will also give you 0.12 pu. Z0 on the other hand is 1.1 into 0.05 upon 1.15, okay, which is 0.048 pu. Okay. So, finally, the equivalent circuit is 1 pu, which is the source, voltage source, then Z1 of 0.12 pu, Z2 is also 0.12 pu, and Z0 of 0.048 pu. Okay. All these three are in series, as we saw when we derived the equivalent networks for different types of faults, and which now gives us IA1 is equal to, this is if we consider it as EA upon Z1 plus Z2 plus Z0, which is 1 upon 0.12 plus 0.12 plus 0.048. Okay. So, this gives us 3.472 per unit. Okay. And the total fault current, which is IA, I fault, which is IA, is given by 3 IA1 is 3 into 3.472 per unit is equal to 10.416 pu. Now, to calculate the fault current in amperes, we need to this I fault in amperes will be 10.416 into I base. What is I base? I base is the base MVA in the upon root 3 into base kV. Into 1000, of course. So, this will give us 100 upon root 3, and since the fault is on the 115 kV section. So, we will take 115 as the fault MVA. Okay. So, this gives us 502 amperes. Okay. So, the total fault current in our case IF or I fault is equal to 10.416 into 502, which is 5229 amperes. Okay. So, this is the total fault current if there is a single phase to ground fault at bus G. So, we will quickly see the fault current for the fault at bus H. Also, the second part of the problem is find the fault current for a SLG fault at bus H. Okay. There is one more part, which is finding the fault current at the midpoint of the line, which we will leave for self study. I will just draw the sequence networks in that case and then leave it for self study. However, we will see the calculation for fault at bus H, which is this bus. So, in this case what happens is we will modify the above networks and we will proceed a bit quickly on this. This is 0.1, then the transformer is 0.05, I believe, yeah, 0.05, then this is the bus G where at which the fault we calculated. Then we have the transmission line of 0.3 pu. All the values are in pu. I am just dropping it for the sake of convenience. This is 0.1 pu. Is that right? Yes. Transformer is 0.1 pu, and the source here is 0.24. The negative sequence is the same as earlier also. So, we have 0.1, 0.05 bus G, 0.3, 0.1 and 0.24. The zero sequence will be different, similar to the last part of the problem, and that will give us no, this is not given, but does not matter as we said last time. This is 0.05 bus H, 1 bus G, sorry, bus H, and 0.1 this is open. As of last time, these two are open since there is a delta on that side, and then this we connect to the reference bus or ground. Okay. So, we in this case we will do a very quick calculation, not very detailed. Okay. So, in this case we will have 0.3 plus 0.05 plus 0.1, 0.3 plus 0.05 plus 0.1, 0.45 in parallel with 0.24, 0.34 rather, sorry, I have missed this, 0.1 plus 0.24. In this case also it is similar. So, 0.45 in parallel with 0.34, and in this case it is 1.05 in parallel with 0.1. So, our equivalent sequence circuits will look like this. It will be 0.45, 0.34, 0.45, 0.34 and 1.05 parallel with 0.1. Okay. Okay. IA1, which is the fault. Now, note that though it is not asked in this problem, since we have the impedances, we can also find the currents which are contributed from each side of or each branch. Okay. Though it has not been asked here, because you have the relative ratio of the impedances, we can easily find what are the contributions from the individual branches, or rather the individual sources in this case. So, here Z1 is 0.45 in parallel with 0.34, which is 0.19 pu, Z2 is the same 0.19 pu, and Z0 is 1.05 in parallel with 0.1, which is 0.091 pu. Okay. So, in this case, if you see the total fault current, which is 3 IA, is given by is around 6. If you plug in the values, you will get this 6.36 pu, and the base current is the same as that as what we calculated earlier. So, the total fault current in amperes is 6.36 into 502 amperes, which is 3197 amperes. Okay. So, now the final part is which is midpoint of the line. Now, for midpoint of the line, I will just draw the sequence networks and then leave it for self study. You can do the calculations yourself. I will just draw it and then the final calculation you can attempt. Okay. So, these are the two sources. By now, we are familiar with the values. So, this is 1 pu, of course, the source. This is 0.1 pu. This is 0.05 pu. This is the bus G, and since it is the midpoint of the line, we will say the midpoint is M. Then this it divides the line into two. So, this is 0.15 pu and 0.15 pu, since the total again total positive sequence impedance is 0.3 pu. Again there is a small mistake here, it is 0.05 pu, not 0.5 pu. Okay. And after that there is the bus H, then the transformer of 0.1 pu, and then the source 1 pu and 0.24. Okay. And since it is the midpoint, the negative sequence impedance network will be the same without the sources, of course. So, this is 0.1, 0.05, 0.15 and 0.15, GMH 0.15, 0.1, 0.24. Similarly, for the zero sequence network, now we will have this branch will be open like always. Then this is 0.05, and now the zero sequence impedance of the line is 1. So, you have 0.5 here, 0.5 here, bus H, this is bus N, 0.1, this branch is open, okay, and then this you connect to the reference bus. Okay. So, if you see Z1 here will be a parallel combination of 0.2 plus 0.1. So, that is 0.3 and 0.39. So, eventually you will get the negative sequence equivalent network will be the same. So, you have 0.3 and 0.39, and here you will have 0.55 in parallel with 0.6. This is 1. Okay. So, you can calculate the final fault currents here. One thing you will notice is that the fault current in this case will be quite low, because that is because the zero sequence impedance of the line has come into the picture. Earlier what was happening is the total zero sequence impedance was quite low in this case, if you see, and that is because there is no zero sequence line impedance which is coming into the picture, and that is why the single line to ground fault currents are quite high. Here if you calculate, you will notice that since the line is coming into picture here, the zero sequence impedance is high, and consequently the single line to ground current will also be low. So, please do this as a self study for yourself, and then we will now move on. We have some portion left from our earlier set of slides that we will complete, and then we will go on to overcurrent calculations. Okay, so this is we have completed this. Okay, so we had from here we had stopped and gone to the problems that we solved just now. Now, when you are looking at solving these circuits using a computer, this is how you will formulate the problem. Here, if you see, these are in phase coordinates. This is I1 to IN, a set of I currents which are ABC, 3 phases, so 3 currents here, and correspondingly the voltage vector is given by V1 to Vn. The V1 itself consists of 3 rows, VA, V1A, V1B, V1C, and so on for the n voltages. Here, this Y matrix here is, if you see the entries here, Y11 ABC, Y12 ABC, all of these are 3 by 3 matrices, and this formulation is similar to that you will encounter in a load flow program, where I is equal to Y and V bus, Y bus into V bus. So, this you can decouple. Networks are generally balanced. So, there is a small difference in the Y bus for a short circuit program and a load flow program, which we will see shortly. Coming back, these are in phase coordinates. We can decouple these using our sequence transformation. The T is a sequence transformation matrix which we saw, that 1 1 1 1 A square A and 1 A square, and this each T is of course a 3 by 3 matrix, and then because it is a block matrix here, the overall transformation matrix will also be a block matrix here, and then this will give us the bus voltages and currents in a symmetrical component domain. So, and assembling that together, the first equation will now be I0, I1 and I2. These are the bus currents and voltages V0, V1 and V2, and they are decoupled. So, I0 is equal to Y0 bus, V0 bus, I1 bus is equal to Y1 bus, V1 bus, and I2 is equal to Y2 bus, V2 bus. Now, you can to solve for the short circuit currents at a particular bus, you need to find the equivalent Thevenin impedance at that bus, like we just saw in the problems that we solved. Now, if we were to do that using matrix inversion, it will be computationally very expensive. So, now what is done is after the Y1 bus, Y2 bus and Y0 bus are assembled or built, then all in the I bus vector, all other currents other than the bus at which you are trying to solve for the short circuit current, let us call it bus I, all other currents are taken to be 0, only the I or the current at the ith bus is taken to be 1 per unit. So, if, what you are doing is you are getting a column of the identity matrix, the ith column of the identity matrix, which is donated by EI. So, this will simplify the computation. What we will do is, then we get, for example, first if you are solving for the 0 sequence currents, then we will get y bus 0 into v bus 0 is equal to EI. Then from that we will do a LU decomposition or a sparse LU decomposition. This is very efficient computationally, and get ZII or the impedance at the ith bus. And similarly ZII1 and ZII2, and then we can proceed using our, if it is a single line to ground fault, then proceed using a series connection. If it is a double line to ground fault, then have a parallel connection, and so on. So we have the fault current formula. We can, once we have got the Thevenin impedance at that particular bus, then we can use that the standard fault current formula to calculate the fault currents. The way that the fault, say at the middle of the line or any point of the line, is calculated is a phantom bus is introduced. Though there is no bus, like we just saw, the fault current at the middle of the line. So we make a virtual bus or a phantom bus at the middle of the line, say M, and then that divides the line into two impedances, and then we proceed to find the Thevenin equivalent. Okay, so one way in which the Y bus is different is that if in the short circuit analysis, that is the SCA as compared to the load flow or the power flow analysis, is that load flow analysis generally, unless it is an unbalanced load flow, will use only the positive sequence matrices. The negative and zero sequence matrices are not used. Secondly, in a load flow program, the voltage at the generator terminal is assumed to be fixed, which is not the case here. Here you use the transient or the subtransient impedance, as the case may be, and then the generator internal voltage is also modeled. So here it is handled like this. If you see, in the load flow program, we are interested in only the V, the terminal voltage, but here we take the internal voltage and the impedance, which may be the subtransient or the transient, as the case may be, what depending on the fault that you are calculating, and then it is converted into a Norton equivalent, and at that bus the entries are made into the Y bus. So this is the difference between the Y bus of a short circuit program and a load flow program. So we will conclude our discussion on calculation of short circuit currents and MVA using symmetrical components. This is how we have actually used this in the calculation, but just to summarize, the three-phase short circuit MVA is the fault current in per unit into the three-phase base MVA, and the single phase short circuit MVA is the short circuit current in per unit into the three-phase base MVA. Okay, so we will now go on to the next topic. This concludes the initial part where we saw the properties of the protection system, and then I had a look at the symmetrical components. Now we will go on to the individual protection paradigms, that is overcurrent protection, distance protection, etc. So we will start off with we'll start off with overcurrent protection. Before we get into overcurrent relaying, we will have a very brief look in today's class on fuse protection, and then from the next time we will see overcurrent relays also. Now, before we get into fuse protection, we will again have a brief revisit at the faults and type of faults before we then move on to the fuses. If you see, this is actually a sort of a modification of the state transition diagram. It shows the states in which the power system can operate. One is of course the normal or the healthy state, where all the voltages and currents are within the limit, say 0.95 pu to 1.05 pu, that is the voltage the currents do not exceed the ratings of the equipment, etc. Then there is an abnormal state where you have the voltage or the currents exceeding the normal operating ranges, but it is not high enough or low enough to be classified as a fault. Then you may have a faulty state where the currents are extremely large or the voltages have dropped to 0, and this usually in a power system is a temporary fault, a tree branch touching or something, then it goes back or it is burnt off, then the fault clears on its own. So, from a faulty state the transition can go back to normal state without operating any relays or circuit breakers or any other equipment. But if it is a permanent fault, there is something that has fallen, some metal portion that has fallen on a line or something like that, then it may be a permanent fault. It may not go off on its own, or it may not be cleared on its own. Then in which case the line has to be tripped, or the transformer has to be removed from service, or the generator has to be removed from service. That is, the equipment has to be isolated. Then once that equipment is isolated, because there are redundancies present in the network, the system goes into a restorative state and then comes back into the normal state after the equipment is brought back into service. So, this is how the state transition diagram looks like for faulty and non-faulted states. The problem with the faulted states is, of course, the voltages and currents are far exceeding the limits that the equipment are supposed to operate in, so that it may be unsafe to operate in these regions. Also, it could lead to permanent or temporary or permanent equipment damage. It could lead to fire and other issues with safety. Sources of fault currents we have recently seen. From the fault calculations that we did in today's class and in the last class also, we have seen that the magnitude of the fault current depends on the sources themselves. Whether it's a weak source, that is the impedance is low. The other way around. For a weak source, the impedance will be very high. For a strong source, the impedance will be low and the contribution will be high. Then if there are any transformers in between, then what are the transformer impedances, and distance of fault from the source. So, because if there are transmission lines and the distance is high, then the transmission line impedance also comes into play. Motor contributions, sometimes it is ignored, but if you want to be totally accurate, then motor contribution also needs to be considered. As a quick calculation, the transformer short circuit, if you want to find the short circuit level at the transformer secondary, you can simply do it as 1 by Z into the full load current. That will give you the fault level at the secondary of the transformer. If Z, that is with Z in PU, if Z is in percentage, then you have to multiply the current by 100. Okay. So, now we will move on to the first type of protection that we are encountering in this course, that is the fuse protection. Now, this is rather overcurrent by far is the most widely used kind of protection. It is present in almost all the circuits, even when there are other types of protection present like distance protection or differential protection. A plain overcurrent relay will invariably be provided as a backup relay. So, it is the most widely used kind of protection, and within the overcurrent protection, fuse protection is also very widely used. Fuses are there everywhere. Till very recently they were there in our houses also, in residential places also. Now, they have been replaced mainly by miniature circuit breakers, but otherwise we have widely used fuses. They are there in your 2-wheelers, 3-wheelers, any equipment also will have an overload kind of fuse. So, a fuse usually consists of a fusible device. A fusible device means a part which melts when the current greater than its rated current flows through it. Okay. this, because of the resistance of that part, once the high current flows through it, because of the I square R into T loss that is taking place, the enough heat is generated and the fuse will melt, and by which it will open the circuit. There is no note that unlike in a relay, where a relay is associated with a circuit breaker, and a relay will take the tripping decision and will pass that decision to a circuit breaker, which will then open the circuit. Here in a fuse element, the fuse element will itself melt and open the circuit. So, there is no separate circuit breaker, which means that you do not require a DC supply and other kind of CT, PTs, etc. You do not require a substation kind of arrangement, and that is why it is very cheap, and that is why it is very, very widely used also. You may have seen fuses being used with transformers mounted on poles, etc. When you travel out in cities, they are nowadays they are being replaced by underground transmission, but otherwise wherever transformers are mounted on poles, you can see the fuses on above that transformer. Okay. So, the fuse has two characteristics rather. One is the melting characteristic. When the fusing element melts, and the circuit is not interrupted at that instant. You have to, though it may seem otherwise, but then an arc is struck, and the circuit will be opened only when that arc path is deionized. Okay. So, it is much like your switchgear. If you have studied switchgear earlier, we are not going to look at that in this course, but an arc is struck and then that path also has to be deionized. Okay. So, then there is a thermal characteristic, which is the melting characteristic, and an interrupting characteristic, which is the overall interrupting characteristic from the initiation of the fault to the opening of the circuit. Okay. So, the thermal characteristic consists of the current rating of the fuse and the melting characteristic, when the current is high enough for the fusing element to start melting. Okay. The interrupting characteristics, on the other hand, there will be a voltage built up across the open contact. So, then it consists of a voltage rating and an interrupting rating. Okay. So, we will have a look at the thermal characteristic. If you see here, as we said, it is the I square RT. So, if you take that as a constant, then the melting time of the fuse will be inversely proportional to the square of the magnitude of the current, and this is provided by the manufacturer. You can see that this is what we call extremely inverse. We will come to that when we study overcurrent relays, what is extremely inverse, what is normal inverse, what is very inverse. But keep in mind now that these are extremely inverse characteristics, and this is the melting characteristic, not the interrupting characteristic. Okay. The interrupting characteristics is we will come to that. Now, that depends on as we said, once the fusing element melts, there is a transient voltage that will appear across that contacts. So, that it should withstand this and the recovery voltage, and since the fault currents is mainly inductive because of the nature of the circuits, that the X by R's, etc., the arcing time, the stored energy can be large, and then the arcing time can be large, and the total melting time and arcing time together gives us the total clearing time, or the TCC. Okay. So, these TCC curves are also available from the manufacturer, and this shows us the TCC curves. They are similar to the melting curves, but not exactly the same. Okay. Now, these curves are important because if we need to coordinate relays with fuses, then we will be using these curves. What is coordination, we will see maybe in the next class or the class after that. Okay. So, this gives us the total clearing curve or the total clearing characteristics of the fuse. So, depending on the current, the clearing time can be obtained using this characteristic. If you notice here, these are plotted on log sheets. That is because if you want to compress a lot of information in a small graph, then you can see the range here is from 10 or 1 or 10 to 10,000. So, the ratio is about 1000. Also, here the time in seconds, if you see, is from 0.01 seconds to 1000 seconds. So, that is also 10,000 or even 10 raised to 5 times. So, to compress all that into one sheet of paper on a linear scale is difficult. So, that is why a log sheet or a semi-log sheet is used. Okay. So, now generally current fuses, fuses are non-current limiting fuses. There are current limiting fuses also, as we will see very shortly, but these are the majority of the fuses are non-current limiting type of fuses. So, here they are generally of two types, where you have expulsion fuse, where what happens is the material around the fuse is such, inside the fuse is such that once the arc is struck, some gases are formed, and this gas, because they are packed into a small volume, this gas will be generated and pushed out at a very high pressure. So, that this will help to constrict the arc channel and eventually extinguish the arc, and also help in building up the dielectric strength. But these cannot be used where the gases which are caused by this action of the fuse can lead to some fire or some maybe a hazardous condition, like in a chemical plant or something. Then in which case vacuum fuses are used. It is a vacuum fuse, as the name suggests, is a completely sealed unit with vacuum inside, and no expulsion gases or etc. Are generated. Now, this is the current and voltage time relationship of a fuse, of a expulsion fuse or a non-current limiting fuse. If you see this is the first part, as is shown as the melting time, and after the fuse has melted, then depending on the X-bar ratios etc., the current will be interrupted close to the natural current 0. Okay. So, it does not force the current to 0. On the other hand, the current limiting fuse that we will see right now is actually there is some material in the fuse, which once the element blows, this introduces a very high resistance in between the contacts. So, which forces the current in phase with the voltage, and the current is quickly extinguished. Okay, because a very high resistance is introduced into the circuit, and the path gets completely deionized very quickly. Could be material like sand or silica sand or something like that. Okay, if you see this is how the current limiting fuse looks like, and generally the fuse is filled with sand. Around the fusible element is filled with silica sand. So, if you see the characteristic here, this current, which would have earlier followed the dotted path if the fuse was a non-current limiting fuse, will now actually force to 0 at this point here, okay, or close to that point there. So, this current is known as a prospective current here. This peak is known as a prospective current, while the actual current is brought down to 0 much earlier. So, where there is a need to limit the fault current, this type of fuses are used. Note that an overcurrent relay will not do this. So, unlike relays, you can limit the current using fuses. Of course, there are fault current limiters and all that, but we are not talking of those elements. On its own, a relay will not limit the fault current, whereas a current limiting fuse can limit the fault current. Another distinction is depending on the voltage and the circuits in which the fuses are applied, they are classified into power fuses and distribution class fuses. As the name suggests, they are used. Power fuses are used generally where close to generating stations, etc., while distribution fuses are used in distribution circuits. So, this is the equation. We are not going to go into too much of detail, because we are actually going to study the overcurrent relays in greater detail. So, this is the equivalent circuit of fuse, and if you see E arc is the voltage across the arc, and the inductance in the circuit is given by L. So, this is the governing equation V minus E t, E arc is equal to L di by dt, and the current can be found by integrating the above. Okay. So, we can see that the current is proportional to area under the difference of source and arc voltage, that is the integral of that. And if there are this also implies that if there is a higher source voltage, the interruption will be affected. Okay. On the other hand, high arc voltage will limit the, because there is a minus ERT, will limit the fault current. Okay. So, we will, this is how the arc current waveform looks like. So, to summarize, we saw the what are the faults and abnormalities, then what are the sources of fault currents in today's class and the previous classes. We looked at the fuses for overcurrent protection, and then we looked at some characteristics of the fuse. Now, we will quickly have a look at the fundamentals of overcurrent protection before we stop for today. Okay. That is, we will start off with limitations of the fuse, and have a quick look at the algorithm for overcurrent protection before we stop. So, the first, the advantage of a fuse, of course, is that it is very compact. You do not require substation like arrangements where you have power supply, DC and DC supply, CTs, PTs, etc. It is directly fits into the circuit and can trip and can clear the fault. On the other hand, this also makes it difficult to remotely close the circuit or something like that. The maintenance crew has to go to the site, see what the fault is, replace the fuse, and only then the circuit can be energized. So, that is while it is an advantage in some cases, it is also a disadvantage because it leads to longer outage times, and there is no remote operation possible. Also, it is unlike a relay where you can set a timer, etc. We will see that very shortly in the next class, where you can set the time to trip. In the case of a fuse, you can't do that. It totally depends on the fusing element. So, it is difficult to control the exact time to trip, and that is why it makes a coordination between fuses or even fuse and relay are a bit difficult. So, primary and backup coordination is a bit difficult. So, that is why where there is more precise control, etc. required, we use overcurrent relays. We will have a quick look at the algorithm for overcurrent protection before we stop for today. The first part is, of course, finding the threshold for the current, which is the IRF. Then the actual current for the equipment or the device is measured, which is I. Then the ratio I by IRF, I means what the measured current upon the reference or the threshold current, is known as a plug setting multiplier. Now, this is because why plug setting multiplier is because the overcurrent relays of the electromechanical type actually had taps where you could set this, and you had to set the plug. Plug was removed and inserted. So, that is why it is known as a plug setting multiplier. In the next class, maybe I will show you a picture of this. And then if the PSM is above a particular threshold or above the threshold, then the relays issues a trip command. So, this is how the algorithm looks like. First, the device current is read, and then it is compared to the reference current, and then because we are using a adder or a subtractor here, we will see the sign of that. If it is lesser than the reference current, then of course you go back and measure the current again, and it continues to measure the current in a loop. If the measured current is greater than the reference current, then of course it sets a on timer, or it starts the timer, and then it actually goes back, because you don't want to trip the relay, or rather issue a trip command for even for one instance of the measured current being greater than the reference current, as that may be some transient or something that would cause nuisance tripping. So, generally you need to check for a required interval of time. So, it checks for that, and then if the counter itself has run out, then it will issue a trip command. So, this is in very brief the algorithm for an overcurrent relay. We will stop here. We will discuss this and the overcurrent protection in greater detail the next time. Thank you.